Where should they be placed? They should be densely concentrated in the area where injection is occurring, at least initially, just to assure that nothing is going on. There are many experts about how to deploy a seismic network, Professor Prieto being one of them. Usually the networks are 8, 10, 12 seismometers. There are different kinds of seismometers. There are different ways to deploy them. So the details will change, but that's about the scale of the operation you're talking about. Within, say, a 5 to 10 kilometer radius of the point of injection, you'd probably want to put somewhere between 8 and 12 seismometers if you're concerned about the injection potentially triggering seismicity.
La siguiente pregunta es, ¿qué autoridad realiza el seguimiento de los sismos potencialmente causados por la inyección o por el fracturamiento hidráulico en los Estados Unidos?
That's a very good question because no one is in charge. And right now, it's recognized as a major failing of the regulatory system. These earthquakes that occurred in 2011, are what got everybody's attention, and there have been no regulations put in place. Now, I fear this vacuum. I don't fear it as much as the oil companies fear the vacuum, because the easiest thing for a regulator to do is to establish some arbitrary criterion, and if that criterion is exceeded, to simply stop operations. That's what happened in England when that magnitude 2.3 earthquake occurred. That magnitude 2.3 earthquake was not felt by a single person. It was detected by the regional seismic network, and they still closed everything down for 18 months. That's why I recommend, for industry and regulators to work together and be proactive and to collect the data and to establish what a risk assessment looks like. You understand the local geology, you understand active faulting in an area, and you can set criterion in advance, saying, well, if we see a couple of earthquakes of small magnitude, we're going to pay a lot more attention. If the earthquakes start to line up along what may be an active fault, we may reduce the injection rate. If the earthquakes keep going and the magnitudes increase, we may stop the injection rate. Okay? But it's something based on scientific principles. It's something based on good measurements, good observations, and it's something that's thought out in advance. Because right now, I can tell you what happens in the United States. If there looks like there's an earthquake triggered by injection, first thing that happens is the oil company denies it, and the regulators go into a brain freeze. They don't know what to do. And that's a scary situation for everybody because they could easily overreact when there's really no danger at all. And that's why the geothermal community, in which small earthquakes are very common in geothermal sites, wanted to develop this stoplight system so that when something happens, we don't immediately stop everything, but we are cautious. We do pay more attention. We really assess the risk very carefully and then decide if it's safe to go on.
De acuerdo con su presentación, ¿se podría decir en conclusión que un fracturamiento solo puede producir pequeños terremotos cuando hay una falla presente?
Yes, that's exactly the point I was trying to make. I should say that the conclusions that I just presented to you were exactly the same conclusions of the National Academy Committee report that I referenced early in my talk. They said with hydraulic fracturing, the chance of triggering earthquakes was extremely small, the risk was extremely low, and the public was in no danger whatsoever. With respect to wastewater injection, the risk to the public was still very low, but by being more careful, more proactive, that risk could be lowered even further. And then they went on to talk about CO2 sequestration, which we're not talking about at this meeting, but they pointed out that because the volumes are larger and you're injecting over longer periods of time, that was a more problematic situation. But they fully, their conclusions and the conclusion, my personal conclusions that I presented to you were identical. With hydraulic fracturing, extremely small risk. If anything starts to happen, you can see it immediately. You can stop the injecting, and the problem immediately goes away. With wastewater disposal, you have to be a bit more proactive, and using some intelligent form of the stoplight system, you would have time to assess the risk and make a scientific judgment about whether operations could continue, operations should be altered, like injecting at a lower rate, or operations should cease.
La siguiente pregunta es, ¿qué tan lejos o qué distancia mínima deben tener los pozos de disposición o de inyección de agua residual de los sitios del fracturamiento?
I don't think it really matters. You're not going to be injecting wastewater into the shales because the shales have such low permeability. But if you could drill deeper, for example, and find a good formation for injecting, those two levels, they're not interacting with each other, so they could be right next to each other. I don't think there's any real issue. I do think that you want to have an idea through modeling of how far that halo of pressure associated with injection extends that I showed you in that one modeling exercise. But in principle, there's no distance required because you're dealing with different stratigraphic levels.
En la fase de exploración se realizan pozos de fracturamiento y es necesario realizar monitoreos de sismicidad en esta etapa.
Yeah, is it necessary to monitor microseismicity during the exploratory or the initial hydraulic fracturing? Absolutely. In fact, that's when it's most valuable. The microseismicity is going to tell you how far the hydrofracts go. They'll tell you how high they go. You want to know how far they go because you want to have an estimate of the well spacing. And so microseismicity is almost always monitored in the early stages, and so you'll discover there if you have any problem with pre-existing faults, etc.
Sorry.
So I want to ask you a question about this particular point. When you look at the cloud of microseismic events that pops up after you've done one of these local individual fracturing, it may have a lot more information in it than just signaling a nearby or prospective fault. It may have, indeed, the bizarre pattern of it suggests that it may have information that would lead you to do your subsequent fracturing differently in order to have a more efficient, complete operation of removing hydrocarbon, thereby getting much more efficiency in the operation.
That's absolutely right.
Who is doing that?
Nobody is doing it as well as they should be. It's an area of research. It's an area where the different service companies kind of compete with each other. But it's absolutely right, because just think you have a well that's, say, 5,000 feet long, which is a typical length. Right now, the rule of thumb is that the frac stages, the distance along a well that's pressurized at the same time, that stage is typically modeled on the thickness of the shale. It's just kind of an arbitrary rule of thumb. But if those microseismic events don't go very far from the frac, you might want to make the stages much closer. If the cloud is very big, you could put the frac stages further apart. So you get a lot of valuable information from the microseismicity. And of course, it'll tell you whether or not intersecting pre-existing faults is something to worry about.
Para la siguiente pregunta probablemente hay que dar un contexto para contestarle. En Colombia se define un área de influencia alrededor de un proyecto sobre la cual puede haber impactos, a partir de la cual se toma la información, digamos, es un perímetro a partir del cual se toma la información de línea base de todo el proyecto. La pregunta está relacionada, digamos, dando por sentado o dando por hecho que el metano podría, debido a la microsismicidad inducida o triggered, no sé cuál es la exacta traducción, el metano podría migrar a los acuíferos y contaminarlos debido a la sismicidad, dando eso como un hecho, digámoslo, habría que saber si eso es correcto científicamente o no. Entonces, se debería tener en cuenta para definir esta área de influencia toda el área donde podría causarse fenómenos de sismicidad.
Before I answer the question, is it in regard to hydraulic fracturing or wastewater disposal?
Fracturamiento hidráulico.
Hydraulic fracturing. Okay. Let me show a slide from Professor Deutsch's presentation. It seems like a long time ago, but it was just this morning. Thank you. Okay, so the red line here is the depth of the Barnett Shale. So there are like 2,000 wells here, and they were ordered from the shallowest to the deepest, okay? And what you can see, as Professor Deutsch pointed out,
la siguiente pregunta está en inglés, voy a traducirla al español.
oh,
El shale de Barnett y el shale de Marcellus está en una posición distal, lejos de la formación de los Apalaches, que es una formación antigua. Colombia está en una región muy activa tectónicamente. ¿Usted realmente cree que la información que usted está presentando aplica en este caso?
yeah, I think the information I presented I tried to present it as a generally applicable framework. So, for example, if you're in the Llanos Basin, where there are relatively few earthquakes, or if you're along the foothills belt, where there are more earthquakes, you're obviously going to be more concerned along the foothill belt. But the principles still apply. If you're going to put a wastewater injection well somewhere, you want to make sure you choose the right kind of geologic formation. You want to make sure you're avoiding active faults. You want to make sure you're monitoring what's going on. It becomes perhaps a little bit more important when you're along the foothills belt because it's more active than other areas. But the framework I tried to outline is broadly applicable, but you just pay more attention in some areas because it has, it's just more active tectonically than perhaps, in others. So.
Muchas gracias, Dr. Sobak. Thank you.